Okay, so good morning to all of you. Today we will talk about the impact testing of a material. And when I talk about the material, that means we can consider the metallic material as well as non-metallic materials also. So we know the best purpose of doing impact testing because in the very first class we talked about the situations where material can experience the impact loading. So basically, we want to study that how the material behave under the impact loading conditions. Okay, so here is the two most distinguished examples which reflects us, which reflects that the material behavior under impact loading conditions. Okay, so this particular examples you can find in the literatures where a sieve has broken into two parts, simply two parts. Okay, in Second World War situations. Uh, Now, at that period of time, people were unable to understand that though they have made the safe, which is made of steel and high strength steel, but why this safe broken into two pieces. So at that period of time, it was very difficult to understand. But gradually, when fracture mechanics come into the pictures and the development of fracture mechanics, comes into the pictures, then people generally understand that there are several factors that can influence the you know materials behavior or materials deformation mechanism, and that lead to the failure or the fracture of a material. Now here I am talking about the two different terminology, that is failure and the fracture. So can you differentiate these two terms, that is failure and what is fracture? Are you listening? Hello.
Yes, sir.
Can you differentiate the failure and fracture? What do you mean by
Sir,
failure?
failure is that it has failed the purpose, and fracture is the
Okay.
complete breakdown of the material.
So complete breakdown means it can separate into minimum two pieces, right?
Yes, sir.
Yes, sir. The
Yes,
physically
go
it
ahead.
has broken into two pieces, at least.
Okay. Okay. But the failure means either the fractures can happen or may not happen. Okay. Let's say I'm talking about the design of the aircraft blade. Okay, so in that particular cases, the design is very stringent and very specific. So if the blade of that particular aircraft engine extend a little bit, then it may collide with the surrounding walls, and the failures may happen. Okay, or the engines may shut down, or the fire can spread out. Okay, so that lead to the failure. Or some cases you will find that um, if you hold a material mm, uh, for a longer period of time. Okay, though the load may be a little bit less as per your capacity, but you cannot hold it for a long time. Okay, uh, you know means opposite to the gravity. Okay, so in that particular cases, you can say that you are unable to hold that weight for a longer time, so you fail. Okay, so I can give another examples, like you give an exam, and then you are unable to pass the exam, so that is one sort of fail. Sometimes if I compare the examinations with brilliant students who have not got the 90% or 80%, so that is also a failure for brilliant student. So in that way we can define the failure. But the fracture is completely different things, means materials will separate into minimum two pieces or more than two pieces. Okay, so here you can see that the fractures of the sieve has happened. But people at that period of time, they are unable to find out the factor. So gradually people think and find out that at that period of time in Second World War, when this kind of incident has happened. So think about the environment. Okay, so environment and the load that impacted on the ship. Okay, um, and they are trying to correlate this thing. Okay, so two important factors they have found out initially, that is the temperatures, means at what temperatures the ship is situated there. Okay, and the impact loading, that is the ballistic loading, or the bullet impacted on that particular ship, or the heavy loaded things has impacted on the ship, so that lead to this fracture. Okay, there is another examples you can think of. The first one, okay, that is the pressure vessels, and here also the pressure vessel has break, and not completely fractured but break a little bit, and the failure has happened. Okay, so here though impact load has not applied, was not applied in that particular cases, but some static load can also influence the fracture. Okay, fracture of a specimen. So though we are studying the situations of impact loading conditions where the material behave differently, but still we will also study that how during different types of loading, how the material behave and material fracture from ductile fashion to brittle fashion. We already studied during tensile test that if you do the tensile loading, or if you apply the tensile loading, the material generally fractured, or the materials generally separate into two pieces under ductile fractures manners. Okay, and how you know that the material has failed under ductile fracture manners? If you characterize the fracture surface thoroughly and carefully, then you will find some dimple kind of fracture. Microscopically you will find the dimple kind of fractures, and by seeing those fracture surface you will understand. And macroscopically if you see, then you will find some cup and cone kind of fracture. Okay, in your open eyes you can, by seeing those things, you will understand that the fractures generally happen under ductile fashion, because at that particular cases the loading rate was relatively slow or relatively low. But here in impact situations, if you think of the loading rate, then relatively it is very fast. Okay, so that is why, though same amount of load in tensile test are resulting the ductile kind of fracture, but in impact conditions where high amount of strain rate you are applying, so in that particular cases maybe material fell in brittle fashion. So here also peoples at that period of time, or gradually even after the time passes, so they have found that the fracture that has happened, it is completely brittle fashion. Okay, so that is the important things in this particular course, that we will try to understand how these transitions generally happen. Okay, and what are the main factors that could influence of the transition in fracture behavior. So considering this first of here, first pictures, though no kind of loading is applied, but the situations is that if a material have a minor amount of crack or any dent, then that may lead to the impact kind of situations. Okay, the impact kind of situations I'm talking about, that let's say you have a minor crack inside the material, then if you know the stress concentration factor, the concept of stress concentration factor, then you will understand that though you have the static loading inside the pressure vessels, but if the load is insufficient to break the cement or break the material, but you have that crack, then at the crack positions or the notch of the crack or in front of the crack, that particular load will that particular load will increase significantly. Means you multiply with such factors, then that is also possible. Uh, um, uh, that multiplied load will influence
Uh, sir,
the fracture behavior. Yeah,
sir, your voice is breaking, sir.
follow.
Yes, sir, it's breaking.
Can you please wait for 1 minute? I'm just changing my network. Just
Okay, sir.
hold on for a second, for a
Sure.
minute. হ্যালো, হ্যালো।
Yeah.
এখন শোনা যাচ্ছে?
Yes, sir. Yes, sir.
Yes, sir.
ঠিক আছে, ঠিক আছে। So here, from the concept of stress concentrations, you can think of that how your applied load will amplify, or applied load will be multiplied to some factors, and that can induce to the crack to propagate, and that can induce the final failure, or that can affect the material to fail. Okay, so here this is the basic equations by which you can think of that if your applied stress is sigma, then at the notch, from at ahead of the notch, how the stress will will increase, or how the stress values will increase, and that can exceed the tensile strength values or the fracture stress values, and that led to the fracture. So if you change the tip radius, or the notch tip radius, then that may also lead to a value of infinity. Okay, so infinity means theoretically it is possible, but practically, before reaching to the infinite values, it will fail. The materials will fail. So overall, if you think of, then you can find out that the conditions for brittle fracture that lies in three different distinguished factors. One is the low temperature, and the second one is the high strain rate or the rapid rate of loading, and the third one is the triaxial state of stress. Now here, you can think of the to understand the triaxial state of stress. You can think of the examples of if you put a balloons inside the water, then you can find out that the pressure that the balloons will experience in all directions, that will be same. Okay, so that means the pressure that experienced by the balloon is the hydrostatic pressure, and that is a normal pressure. Okay, so these things can also be similar to the triaxial state of stress. That means when a material experience normal stress in all three direction. Okay, so then in this particular conditions, if the material fails, or if the deformation happens, then that particular situation is called the triaxial state of stress. Yeah. Okay, so for better examples, if I show you this particular schematic, then I think it will be clear to you. Like if you have a very thin plate, or if you have a piece of paper, then you know that the thickness is very, very small. So if you if you have this crack, or if you have any minor defect, um, at that particular seat, then if you apply the load along the y-axis, then you can find that your based on the loading directions, there must have the stress variations along the length along the width direction, that is the x direction. Okay, so that means there must have certain stress variations along the x directions also, and this stress variation is not direct applied stress but the induced stress. Okay, so but along the z direction, that is the thickness direction, there would be no such kind of stress. So that means in this particular material, if the material failed, then the the failing the failing of this material is responsed by this by this two stress, or the biaxial state of stress, that is sigma y and the sigma x. Okay, but if you have the thick material, then you will find that though you are applying the stress along the y direction, but parallelly, along the x direction, that is thickness, width direction, as well as the thickness direction, that is the z direction, the stress will be induced. And due to having this, all these three stress components, the materials will fail, okay, in different fashion. Here, the two situations, that is plane stress condition and the plane strain condition. But the plane strain condition, it is not that always hydrostatic stress will be there, but yes, the triaxial state of stress will be there. Means all three axes there must have certain stress component, and that lead to the the, the failure of the material. So in order to fail a material under brittle fashion, these three conditions, that is triaxial state of stress in front of the notch or in front of the crack, should be there. That means the material should have the sufficient thickness. Okay, it is not that you are thinking about the failure, or the failure of a plane seat under impact loading condition. That is not, because if you use that very thin material, then due to having the plane state of stress conditions, the material may not fail under brittle fashions. Though you are having very high impact loading conditions, though you are maintaining very low temperature, but material may not fail under brittle fashion. Okay, so there must have three distinguished conditions, and that may lead to the the failure of a material, or the brittle failure of a material. But yes, from material to material, the variations in temperature you will find. Means when we plot uh, the impact energy versus temperatures and the loading rate versus temperature, then we will find that for different material, the energy absorption capacity or the internal temperature is different. So I will show you later on graphic that how these things. So in laboratory scales, how we can measure or how we can conduct the impact test. So there are three different way by we can do that. Like we can do this impact testings following the Charpy testing methods. We follow the ISO testing
স্যার
method,
আপনার
and
কথাটা আটকে আটকে আসছে একটু।
আচ্ছা আমি একটু কেটে দেওয়া রিজয়েন করছি, হ্যাঁ।
ঠিক আছে স্যার।
হ্যালো।
হ্যাঁ স্যার, শোনা যাচ্ছে।
একটু বলবে,
স্যার,
হ্যাঁ হ্যাঁ বলো।
স্যার বলছিলাম মানে why this triaxial state of stress is much more important than the other two factors ওটা আরেকবার একটু বলবেন?
হ্যাঁ, triaxial state of stress means all three directions there must have stress component, right? But in case of biaxial stress, the only two stress component will be there, and if the two stress component will be there, then the fractures mode will change. Okay, that means the fractures will happens more in shearing mode. Okay, in biaxial state of stress condition, shearing and tearing mode. That is why
হুম,
you will not get the fractures that is completely brittle. The fracture surface is not completely brittle. You know that when the shearing will happen, or the shearing kind of things will be there, then uh, uh, then the fracture surface you will get more or less a ductile kind of fracture. Some ductile voids will be there. Okay, so that is why the energy absorptions capacity will vary depending on this different type of fracture. Okay, এবার ওই ধরনের ফ্র্যাকচার মানে শিয়ারিং ফ্র্যাকচারসটা কেন হচ্ছে, সেটা তুমি ভালো করে দেখো যে হাউ this different stress component will affect on changing the mode of fracture from brittle to shearing mode of fractures. So then you will go into detailed about the stress analysis and how they will affect on the fracture behavior. এই পার্টিকুলার পিকচারটা তুমি দেখতে পারো যেখানে দেওয়া হয়েছে লাইক তুমি দেখো when we are applying the load along the x axis, okay, sorry, y axis, then obviously from notch tip to the far end you will find the stress will vary. Okay, now at this particular point, like just in front of the notch, if you see, then you will find that the sigma y values is very high, right?
হুম,
But parallelly, if you find that the sigma x component, which is the induced component, is relatively low or even zero at just in front of the notch, or just ekdom notches samne. Okay, so here what will happen when the sigma y is very high means when the sigma y will reaches to the yield point, what will happen? Material start to yield, right? Though your applied stress is relatively less, means relatively less means I'm talking about the applied stress. Let's say your material is yield strength is 500 MPa. You're applying the load which induced is which resulted the stress component like 400 MPa, right? But the stress concentration factor. So due to having the stress concentration factor, your 400 MPa load will increase, but to a value, and that value will reaches which is well above the yield strength value. Okay, so
হুম,
here I am talking about the sigma y, that values. Okay, now when it reaches above the yield stress, the material start to yield in front of the notch. Okay, and gradually you will find that sigma x values will also increase. Okay, now what will affect the sigma, how the sigma x will influence the fracture behavior? Once the crack propagate little bit, then sigma x will also influence to increase that length of the crack, okay, significantly, and this increment of the crack will happen by shear deformation. Okay, so initially, if you microscopically, if you go into details, you will find that initial positions, what will happen, the crack will extend along the y-axis. That means the crack blunting will happen. Okay, so at few milliseconds or microseconds, you will find that the crack blunting will happen. Okay, and then due to having this sigma x component, again the crack front will shift along the x-axis a little bit. Then again the crack sharpening will happen. Okay, uh, or the crack length, initial crack length will increase a little bit, and the final crack length, whatever you find after a milliseconds or microseconds, you will find that the length will increase. Now, gradually you are increasing the load, and gradually the sigma y will also, the peak values of sigma y will also change. Okay, will increase. Okay, and gradually the sigma x values will also increase and or change, and then after a certain period of time, you will find that your materials will fail, and the crack will propagate from along the x-axis, and the mode of fracture that generally happens due to
shear failure আর কি।
the shear failure, and
হ্যাঁ,
that is why the fracture surface you will find the complete shear fracture, more or less complete shear fracture or
হুম,
ductile fracture. In case of thick material, what will happen? Along with sigma x and sigma y, sigma z component will be there. Okay, and sigma z component along the thickness direction means opposite to the thickness direction. Okay, so it will actually hamper the shear fractures. This with due to having this sigma z component, na, so sigma z component shear fracture take hote debe na. Okay, uh, more or less that will lead to the fracture mode means under brittle fashion. The fractures what will happen, that will happen under brittle fashion. যেরকম বললাম ইনিশিয়ালি থিন মেটেরিয়ালের ক্ষেত্রে প্রথমে ব্লান্টিং উইল হ্যাপেন, ওকে, অ্যান্ড দেন blunting means tip radius will increase, then the crack length will increase simultaneously. Okay, যখন টিপ রেডিয়াসটা ইনক্রিজ করবে দ্যাট মিন ব্লান্টিং হচ্ছে। এবার ব্লান্টিং যখনই হবে মানে ইন ফ্রন্ট অফ দ্য নচ প্লাস্টিক ডিফরমেশন হবে। অ্যান্ড প্লাস্টিক ডিফরমেশন কিভাবে হবে? মানে ডিসলোকেশনস মুভমেন্ট or along the glide plane. Okay, so all these plastic deformations phenomena will happen here. But in case of thick plate, plastic deformation টা রিচই করতে পারবে না due to having this sigma z component. Okay, of course it will depend on the temperature. Like if you do this kind of loading at very high temperature, then obviously the sigma y component will be high enough to reach above the yield strength values, and the plastic deformations will happen. Okay, when your applied load will increase or will reaches above the yield strength value, then obviously plastic deformations will happen. And due to having this plastic deformation, then blunting will happen, crack tip blunting will happen, and the movement of dislocations will happen. Okay, all these sort of things will happen. But if your testing temperatures is a little bit low, or in such a conditions that the your applied stress is not reaching the yield stress values, but your fracture stress, your applied stress will reaches to the fracture stress value. Means your material yields. So that is why you will find that your materials, your applied load is not reaching up to the yield strength value such that the plastic deformations will happen. Material fail before reaching the yield strength values. That is why no plastic deformations will happen, and the materials will fail in completely brittle fashion.
সো প্লাস্টিক
Okay, so
ডিফর্মেশনটা ঠিক ঠিক প্লেটে কেসে হচ্ছে না, তাই তো? মানে প্লেন
হ্যাঁ
স্ট্রেন
থিক প্লেসের ক্ষেত্রে হ্যাঁ হবে না বাট ইট ইজ নট দ্যাট ইট ইজ পারফেক্টলি ট্রু ফর অল সেন্স অর অল কেসেস। যদি তুমি টেম্পারেচার ইনক্রিজ করো সেক্ষেত্রে দেখবে তোমার ফ্র্যাকচার ভ্যালুটা ইনক্রিজ করছে, আর এটা মানে ফ্র্যাকচার ভ্যালুটা হয়তো দেখা যাচ্ছে হিল স্ট্রেংথের উপরে চলে গেছে।
আচ্ছা,
এটা আমি পরে দেখাবো, দেখবে পরের স্লাইডে। তো
এটাকে
তখন
কি
কি হবে যে
আপনার হ্যাঁ বলুন, যা বলুন আপনি বলুন।
হ্যাঁ, so fracture stress মানে fracture stress will precede by the yield strength values. মানে before reaching to the fracture stress values, some yielding will happen, then it will reaches to the fracture stress values, and then material will fail. Okay, or the fractures will happen. আর যখন ধরো fracture stressটা yield strength-এর নিচে নেমে যাবে না, so then yielding will not happen, but the fractures will happen before yielding. Okay, so then no plastic deformations will happen, and when no plastic deformations will happen, the fracture surface you will see that will be the completely brittle fracture.
ওকে স্যার, আর
So
এটাকে এটাকে কি আপনার সাডেন ফেলিয়ার বলে?
সাডেন ফেলিওর বলে যদি লোডিং কন্ডিশনটা ইম্প্যাক্ট লোডিং কন্ডিশন হয়, আর যদি ফ্র্যাকচারটা হয় উইদিন ফিউ সেকেন্ডস অর মাইক্রো সেকেন্ডস অর মিলি সেকেন্ড, ওকে, দেন ইউ ক্যান সে ইট অ্যাজ দি সাডেন ফেলিওর।
ওকে স্যার, ঠিক আছে ঠিক আছে।
Even certain cases you will find that if someone is able to measure the crack growth rate under which happens under brittle fashions, you will find that the crack growths generally happen under the means similar to the rate of sound velocity যেরকম হয় না, so parallelly sound velocity really crack growth rate হয়. Okay, so sometimes you will find in the gate question also that what is the crack growth rate comparing the the velocity of certain things. So you will find that the crack growth rate is equals to the sound velocity.
ওকে স্যার।
Okay, so we are talking about the impact testing, and that can be carried out Charpy testing modes or ISO testing mode or instrumented impact testing mode. So let's see that in three different mode, what are the things that we need to consider. Like impact testing mode, so Charpy impact testing modes, specifically we need to talk about. So for Charpy impact test, first we need to prepare the samples or fabricate the samples from the plate or from the bar, long bar, following the standard, certain standard. So here you can write the standard, that is ASTM E23. So if you go through ASTM E23, there you will find the standard Charpy impact specimen. So first you need to fabricate the specimen to measure the impact energy, okay, at a fixed temperature. Okay, so if you see the schematic of Charpy impactors, so that will be look like, that would be looking like this thing. Okay, now you must have certain impact testing machines. So impact testing machines will be looking like this. Okay, and generally what will happen after preparing the specimens, we need to put the samples, over the anvil. Okay, suitable positions we need to you need to choose. Okay, and then you see that we generally put some notch intentionally such that the localized deformations happen, okay, in front of the notch. Okay, and then and of course whenever we do any kind of mechanical testing, always we consider the worst condition. So that means that the conditions also. That means if there is no such kind of flaw inside the material, then obviously the material performance will be good. But if a material contains any kind of flaw inside the material, so considering that sort of situations, we try to put some notch or some crack in the material, and we try to find out that under these conditions how the materials will behave. Just like the examples of this particular cases, uh, uh, first of all we assume that the material was flawless. Okay, and then we put some gas or liquid inside the vessels, and the gas pressures try to maintain as per the capacity or the load bearing capacity of the material. But certain period of time we see that materials fail. Okay, so why this fail happens? Because maybe inside the material there must have some cracks, and that particular cracks intensify the applied load. Okay, and that may lead to the failure. So considering this particular situations, we try to recreate the situations by putting some notch or some crack in the material, and try to find out that under impact loading conditions how the material behave. Okay, now in Charpy impact test, what we can do, we try to put the samples over the anvil, and then we apply the load in the opposite positions of this particular samples, and then we try to find out the energy absorption capacity of this particular material by seeing the dial. Means if we see the dial very carefully, like here you can see that our laboratory we have this sort of impact testing machines, and then we have the hammer. This is the hammer. Okay, and first what we need to do, uh, we need to put the hammer at the high positions. Okay, and then we release the hammer. Okay, and then we have to put the samples over the anvil. Okay, and then when you release the hammer, it will strike over the material, or it will strike the material. Material will resist to to free flow of this hammer, and this particular resistance will be recorded over this particular dial. Okay, and in the dial there must have certain the energy measurement units, like full counts in terms of joule we can measure those capacity. And then we try to assess the material absorption capacity by reading those dial. Okay, now what is the basic mechanism to measure the impact energy of these things? The impact energy can be measured by measuring the change in potential energy. When you put the hammer at the high positions, and whenever we hammer through that
স্যার
incline like
আপনার
and
আটকে
reaches
আটকে
to a
যাচ্ছে ভয়েস।
Hello, hello. Network এত সমস্যা নেই ভাই। হ্যালো, হ্যালো,
Yes, sir.
Yes,
শোনা
sir.
যাচ্ছে? হ্যালো।
হ্যাঁ
হ্যাঁ
স্যার।
এখন ভালো, এখন শোনা যাচ্ছে।
ওকে। সো যখন আমরা মানে স্যাম্পল মানে পুট করবো না এই এনভিলের উপরে, যদি আমরা ফ্লো করি হ্যামারটা, there should not have any resistance to flow that or to blow the hammer. So then we will find that
আবার আটকে আটকে
the energy
যাচ্ছে স্যার।
absorption should be zero. সরি ভাই, মানে এখানে জানি না নেটওয়ার্কে এত ডিস্টার্ব হচ্ছে কেন। হ্যালো,
Yes, sir.
হ্যালো।
এখন স্যার
Yes.
শোনা যাচ্ছে।
হ্যাঁ স্যার।
ওকে, ওকে।
কিন্তু যখন
সো
বলছেন মাঝে মাঝে ডিস্টার্ব হচ্ছে কেন বুঝতে পারছি না, মানে আটকে আটকে আসছে
মেবি
কথা।
নেটওয়ার্কের প্রবলেম ভাই, এটাই হচ্ছে প্রবলেম অনলাইন ক্লাসে, বুঝতে পারছো?
ওকে 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 স্যার।
So when there will be no such sample, then there is no chance to face any kind of resistance during blowing the hammer. So before putting the samples over the anvil, then we generally check that whether machine is correct or not, and before putting the samples, we try to check that the energy absorption capacity of this particular machines is showing zero values or not. Okay, and if it is shows the zero values, then we can think of that the machine is correct, and then we can put the samples over the anvil in this particular in such a way that the load can be applied just opposite of this particular notch. Okay, and this energy can be measured by measuring the change in height, means after before blow and after blow. Okay, because if you put the samples over the anvil, then it will resist to blow the hammer, and it will change the height, means before the striking, before strike and after striking. Okay, and then if we measure the change in height, then that things will reflect on measuring the material's impact energy absorption capacity. Okay, so IE, that is impact energy, that will be equals to mg into h1 minus h2, where h1 is the initial height, means before striking, and h2 is the height after striking. Okay. Now, depending on the material's impact load bearing capacity, the H2 values will vary. Means H1 is fixed, but H2 value will vary. Okay. And in that way, we can measure the impact energy of different material. So this is the schematic, and where I generally show that how we can put the hammer, or how we can maintain the H1 height. Okay, and if you maintain the H1 height, you will find that at the time of striking, the hammer is achieving the velocity that is near about 5.2 meter per second. So at that particular velocity, the hammer is striking the material, and it leads to the failure of the material. And if you measure the strain rate, then you will find that the strain rate of this particular condition is near about 10 to the power 3 order. Okay, or more or less 500 to 10 to the power 3 orders. Okay, so at that particular strain rate conditions, your material is failing. So that is why you will find that though a same materials, if we do the tensile test, if the ductile kind of fractures will show, but at very high strain rate, that is 10 to the power 3 orders, you will find the material may fail under brittle fashion. Now, how this load can be applied in the hammer? You will find that uh, the, the the load is concentrated over this particular serve tip, and this serve tips will strike the samples. Like if you see this particular schematic, then here you can find that the load basically applied means through this particular sharp tip, and whatever load or whatever weight of the hammer, so all weight will be applied on this particular samples through the sharp tip. Okay, such that the material face the wood's conditions and the materials will fail. Okay, so this is the real examples. Like before the fractures, whatever the samples look like. So after the fractures, the you can find this sort of fracture surface. Okay, and if we carefully analyze those things, then we will find that there are certain regions in front of the notch. There will be certain regions so in ahead of the notch, or from notch front to the extreme end. Okay, so we will characterize these things later on. Now, the placing the samples over the end wheel. This is the end wheel. Placing the samples over the end wheel is a typical task, and if you are unable to place the samples in such a way that the notch tip is shifted towards the left or right directions, then your striking, your hammer will not strike just opposite face, okay, of the notch. Okay, so then the mode of fractures will change. Okay, if you I think Professor PCC have studied about have teach you the different mode of fractures, like the mode 1, mode 2, and mode 3 fractures. So just to recapitulate these things, you can think of the mode 1 fracture is just crocodile mouth opening mode of fracture. Okay, that means once the mouth will open, and that will end up with the complete separations of the two specimen. Okay, or the complete fracture of the specimen. Okay, so these things will not happen if the material will shift means along the horizontal direction. Okay, so that is why we need to follow the standards where they have recommended to use some tongs or like some scissor kind of things, and using this particular things which is called as tongs. So that particular things will help you to put the samples over the anvil in a correct position, such that your striking point will be there just opposite to the notch surface. So here this particular things carefully controlled. Now, coming to the fabrications of the samples, generally in impact testings, we will find that the specimen that generally fabricates maintaining the geometry of 10 cross 10, the cross sectional area 10 cross 10, and the notch is V notch, having the angle is 45 degree, and the notch depth is generally maintained, that is 2 mm, where the notch root radius is generally maintained 0.25 mm. Okay, so this is one sort of conditions, but there must have some other conditions where the severity will increase significantly. How these things will happen? If we reduce the tip radius, then that will increase the severity of the specimen. Means uh, at this particular conditions, whatever the energy absorptions will happen. If you reduce the tip radius, then the material absorptions capacity will change. Okay, so that things we'll study later on, because we generally do this kind of test to measure the impact toughness of a material. Okay, so that is a separate issue, so I'll talk about these things a little bit later. Now, as I said, the velocity, impact velocity, that would be near about 5.2 meter per second, and strain rate is 10 to the power 3, that is generally maintained. And the standard specimen, this sort of geometry we generally follow, that is because to maintain the plane strain conditions or the triaxial state of stress in front of the notch conditions. Okay, so so considering these things, we try to maintain the specimen geometry like this. But yes, people try to follow this particular geometry, um, but if you don't have any sufficient sample, then you can reduce the sample size or you can maintain the subsize specimen. But in that particular cases, the question comes the acceptability of the result. Okay, whether your fractures happen under plain conditions or not. So considering this, people will generally ask you that whether your experiment is valid or not. But yeah, for certain cases, people generally do try to find out the energy absorption capacity. Now here, apart from the V notch, if you follow the ASTM standard, you will find some U notch is also there. Some, this sort of notch can also be there. So as per standard, this sort of notch can also be followed or can also be fabricated to measure the impact behavior of a material. Now, if you same material, if you follow these three different notch conditions, then you can also study the effect of notch root radius on the impact behavior of a material. That means this in order to study the severity of notch root radius on impact energy absorption capacity, then people also can fabricate the specimen in three different ways, that is type A, type B, and type C, and they try to understand that how, depending on the notch root radius, materials will behave. Because this sort of study sometimes required, you can find that certain cases the materials may not always contain the very sharp notch. Sometimes material may contain the crack or the defect that may have certain radius, the tip radius. So considering these situations, the developer, the ASTM standard developer, they have think of to fabricate the specimen in this way. Now, the ISOT test, yeah, the second test, that was the ISOT test. So, ISOT test generally carried out in this particular fashion, though the specimen geometry more or less same, but here you can find that 3 point loading condition is situated, where two positions is there, where that just restricting to move the specimen along the loading direction. Okay, and the another point just in between these two positions is the impact loading point, and so this creates the three loading condition, 3 point loading condition, and that 3 point loading condition is there in case of Charpy impact testing. But in ISOT impact testings, you can find the 2 point loading conditions, where one end will be fixed over the end wheel and the another end will be free, and you have to apply the load in the free end. Okay, and your material should have to put in this particular position such that crack will initiate and propagate quite easily from one end to the another end. But in this use of ISAT testing is rarely available in industry or even in laboratory scales. You will find that most of the cases people are trying to use this impact testing machine, Charpy impact testing machine. Okay, now the difference between the Charpy impact test and instrumented Charpy impact test is that in Charpy impact test, we just try to measure the impact energy absorption by measuring the dial gauge. Okay, but if we talk about the instrumented impact test, then there you will find that certain attachment is available in the Charpy impact test, which can record the load variations with time. Here you can find that when you release the load, no, so then it will pass following this arc, and when it reaches at this bottom position, then it will strike the samples. Means if we fix the time, that is t is equal to 0 at the time of striking, then at the time of striking, when the cracks start to initiate, and then crack will propagate, and that particularly finally lead to the failure. So this whole process, if we measure the time from millisecond to nanosecond to millisecond, then we will find that time t is equal to 0 to time, let's say t is equal to 60 milliseconds, the whole this fracture things has happened. Now within this particular short period of time, if we are able to measure the variations of load, then you will find that the load generally vary in this particular fashion. Okay, in this particular fashion. So is it visible, this particular graph?
Yes, sir. It's visible.
Yeah. So that means here t is equal to 0 means just at the time of striking, and after few milliseconds you will find that the load again come to the 0 position. That means the sample has fractured. Okay. But within this period of time, you can find, or you can see that how the load is varying. Here, this sort of graphs, you can compare it with the tensile graph, where the yield stress is there, the ultimate tensile stress is there, the fracture stress is there. So similar kind of things is happen also here. Okay, where after a few milliseconds or few microseconds, you will find that the your load is increasing to a certain value, that your material is start to yield. Okay. And then that particular things is called the general yield conditions. If your material reaches at this particular positions, then material in front of the notch some yielding will happen. And then it may reaches to the final or the maximum loading conditions, where some sort of plastic deformations may happen in front of the notch. And then it will reaches to the fracture load positions. That means at this, when your load is reaches at this particular position, then material will start to fracture abrupt, and that means abrupt fractures will happen. Here you can find that within a very short period of time, or very means abrupt situations, your material will fail. And and then some residual part will retain there, and that may lead to the plain state of stress, plain stress condition. And then that particular things will lead to the final fracture. So uh, if you see this particular graph very carefully, then you will find that the energy absorption capacity can be divided into two parts, like initiation energy of fracture, or the fracture initiation energy, and the fracture propagation energy. Okay. Now here you need to think of, like, this sort of curve is for a particular temperature conditions. Like, this sort of curves you can find when you do the test at high temperature condition. And if you do the test at high temperature condition, it is not that always you will get the complete brittle fracture. Some a mixed kind of fractures you will find, or even ductile kind of fractures you will find. But yes, fractures will happen. Okay. And the fractures will happen. Now it will depend on the temperature, that what amount of brittle fracture will happen and what amount of ductile fractures will happen. So I will show you the geometry of this particular curve depending on the temperature, that how it will vary. But there are few major points you need to focus, or you need to think of, that if you do the test at room temperature or even high temperature, this important points will arise. And this important point have certain influence on the fracture morphology. Like here you can find that general yield point is there, so that dictates, or that decides, that material will start to yield in front of the notch. And when it reaches at this particular position, so up to this period of time, the plastic deformations will happen, and that lead to that leads to the energy absorptions of a material, which is the initiation energy, or the crack initiations energy of a material. So so if you study carefully the impact energy measurement at very high temperature, then you will find that whatever energy you are getting by reading the dial, so that are mostly you know the crack initiation energy, or the initiation energy of the initiation energy of Charpy, of the Charpy specimen. Okay. A very less amount of propagation energy that is contributing the Charpy impact energy. And this proportion of this initiation energy and propagation energy will vary depending on that temperature. Okay. And that will finally lead to the final energy absorption capacity of the material. So here the point is, when it reaches at the fracture load condition, then the critical crack length of this particular specimens will achieve, and that particular critical crack length will lead to the sudden failure of the material, or sudden fractures of the material. And that means if we see the fracture surface very carefully, then I think it will be clear to you that if you know your material have certain notch, then once the crack will propagate, so up to a certain length the crack will propagate under ductile fashion. Okay. When the initiation energy is significant, and then it this crack length will gradually increase, and it reaches to a final length where specimen thickness will be reduced significant, means residual portions will be there, and which decides the state of stress, that is the plane stress condition. So at the end, what will happen, the materials will not happen, that means no triaxial state of stress will be there, but the plane stress conditions will be there, and that lead to the failure under shearing mode. So what will happen at the propagation, fracture condition, or this propagation energy, what is the significance of this propagation energy? That basically leads to the shear kind of fracture. Okay, so that is why if you see the fracture surface of Charpy specimen very carefully, you will find that some shear lip zone has formed at the end of the specimen, and the surrounding of this material, if you do the test at room temperature. Okay, so in that
এটা
way you
প্রথমে
can
একটা ক্লিভেজ ফ্র্যাকচার ছিল।
বলো।
ওই স্যার ওই যে ছবিটা দেখালেন একদম প্রথমে
হ্যাঁ, আমি দেখাবো ওটা।
ওকে।
ওটা দেখাবো, হ্যাঁ। সেই জন্য আমি বারবার বলছি যে টেম্পারেচার, why temperature is important. Okay. So here this particular test, we can think of that test has been carried out at room temperature. That is why we are getting this sort of load versus time variation. Okay, and whatever energy we are getting, whatever Charp impact energy, the total energy we are getting, so that we can divide this total energy in terms of the initiation energy, where most of the plastic deformation is associated with, and the propagation energy, where the residual length is there. Okay, and that particular residual length is decide the mode of the state of stress, and that is plane stress condition. Okay, and that is why we are getting the propagation energy, and that happens due to the tearing or shearing kind of fracture. And if you see this kind of graph, then also we can correlate with this particular graph with the fracture surface quite easily. Now
Sir,
হ্যাঁ বলো।
sir, what kind of instrument is used to record this kind of load variation for
Actually,
for a
Dynapub. Actually, we can call it as Dynapub. Means instrumented Dynapub, where the signals, actually the light signals we can think of. Generally, কি হয়, যখন এই পার্টিকুলার মেশিনের ক্ষেত্রে দেখবে এখানে একটা ওয়্যার লাগানো আছে না, সো এখানে একটা লাইট কাইন্ড অর ইলেকট্রিক্যাল সিগন্যাল ইজ দেয়ার। সো যখন এই হ্যামারটা পাস করে না থ্রু দিস এনভিল, so how many seconds it takes, so that actually measures. Now যখন তুমি material put করবে over the anvil, so it will it will restrict, or it will change the velocity of the hammer, or it will change the movement of the hammer. Okay, and that things will happen depending on the materials resistivity, impact resistivity. হ্যাঁ, মানে impact deformation যখন হবে, সেই impact deformation যে কতটা রেজিস্ট করছে by the material, so that will influence on the velocity or the movement of this particular hammer, and that can be measured by the electrical signal that pass through this wire and recorded on the computer. Okay, so there must have certain attachment, and that will help to record this data.
thank you, sir.
যেমন ধরো টেনসাইল টেস্ট যখন করা হয় না, সো টেনসাইল টেস্টে আমরা লোডকে কিভাবে রেকর্ড করি, লোড বা টাইমকে কিভাবে রেকর্ড করি, there must have certain transducer or some ওই যে ইলেকট্রিক্যাল পালস যেগুলো হয় না, জেনারেলি তো বাইনারি সিস্টেমে থাকে, যে ইলেকট্রিক্যাল পালসকে আবার ডিজিটালে কনভার্ট করা হয়, বা তোমার এতে কনভার্ট করা হয়, ফলে ওই যে চেঞ্জ ইন the EMF force, electromotive force, so the change in force can be converted to the digital value, that is the stress values or the time value. Timeটা তো ইজিলি মেজার করা যায়, but the load values can be calculated from the change in electromotive force, the EMF force. Okay, or the electrical pulse. Okay, so similar things can also happen here. Okay, to measure the load variations, or to measure the time, how much time it takes to traverse through the anvil. So all these things can be recorded.
Okay, sir.
Acha, so now here whatever the things I have said, like the initiation energy and propagation energy, theoretically we can calculate by knowing the velocity of the hammer. Okay, and by knowing the distance, or by knowing the width of the specimen, that is the x. Okay, so x is nothing but the width of the specimen. Here I think it should be clear to you that there when we talk about the specimen thickness, so specimen thickness means along the notch length, whatever length is there, that is the specimen thickness, and the width is from notch tip to the another end, whatever the things is there, whatever the length is there, so that is the specimen width. Okay, so here x is nothing but the specimen width. So if you know the velocity of the hammer and if we know the specimen weights, then we can calculate, theoretically we can calculate the impact energy, what will be the impact energy. But that is not enough to measure the impact energy of a material. Theoretically it is, we can represent it, but that is not correct in all cases or for all material. So therefore people have tried to rectify it or try to modify it, this sort of situation, of modifying these equations in this way, where the ET is the total energy, and where they have incorporated the alpha values, where alpha values is nothing but the E dash by 4 E0, where E0 is the initial energy of the pendulum. So theoretically it is possible to calculate, but it is not accurately possible, because this the velocity V0 will vary from position to positions. Like before the striking, the V0 will be like 5.2 mm per minutes. Okay, but during striking the velocity v0 will change, so that will lead to the 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 energy absorption capacity of the material. But overall you can follow this sort of equation, not this equation. Now, as I talk about that, this the load versus time variations at the room temperature, but if you do the test at different temperature, from room temperature or high temperature to low temperatures, you will find the fracture morphology will also vary. If you do the test at a very high temperatures, so macroscopically you will find that the fracture surface is little bit dull. Okay, and if you reduce the temperatures, then you will find that the surface are appearing quite shiny. Okay, that means, though if you see microscopically the fracture surface, so here you can find out that the brittle ductile fractures has happened throughout the cross sections of the specimen. And how you can also indirectly characterize these things, you can find that at the tip of the notch, whatever length is there, at the farther end, you will find the length has increased. So people also indirectly calculate the impact energy capacity by measuring the change in length in these two positions. Okay, so these things has already mentioned in the ASTM standard. If you have any interest, then you can go through the ASTM standard and try to understand that how in this indirect fashion we can measure the impact energy capacity, absorption capacity. But here, by following or by seeing this fracture morphology, you can also think of that, yes, the fracture that has happened in ductile fashion. But if you change the temperature from high to low, you will find that this length variation or change in the geometry variations is approaching quite negligible. Means if you do the test at very low temperature, minus 59 or minus 200 degrees centigrade temperature, then you will find that the whatever length it was there before the test, after the test, that length is maintained. That means no such kind of plastic deformation has happened. Whatever fracture or whatever deformation has happened under the elastic deformations region. And that in elastic deformation, the amount of strain is very, very negligible or very low.
Hmm.
Okay, if you think of the tensile curve, then you will find that the elastic region, that the strain is very, very low. But in plastic region, the strain is significant, and
Right.
depending on the amount of strain, the geometry will also vary. Like if your material will fail, means if you are doing the tensile test and if your material will fail under the elastic region, then you will find that the gauge cross sections will be as it is. Means before the test, whatever the gauge cross sections was there, the cross sectional area was there. After the test, that cross sectional area will be same. But if the material experience the plastic deformation, means the plastic strain is there, then the localized deformations will happen, the necking will happen, and then it will reduce the cross sectional area of the gauge portion. So similar things also happen here. Means if the plastic deformations will happen, the shape change, the cross sectional change, cross sectional shape change will happen, and that will reflect on the fracture macrograph. But if the material fail under the elastic region, then there will be no change in the fracture surface or the cross sections of the specimen. Okay. Now, considering these things, if you plot the load versus displacement or load versus time, here I have plotted the load versus displacement. But if you plot the load versus time, the variations will be more or less same. Okay. So don't be confused with this particular slide. So the variations will be more or less same. Like once, if you do the test at low temperature, then you will find that once it reaches at the yield load, whatever I have showed in the earlier slides, then either it reaches the yield load, then the material will suddenly fail. That means the fracture initiation load, if it reaches and which is equals to the yield load, then the material will abruptly fail, or the load will suddenly drop. Okay. And if the load will suddenly drop, then maybe the material will separate into two pieces. Okay. And then the propagation synergy, you will find that is a negligible propagation synergy will be there. If you increase the temperature, then you will find that your fracture load will surpass the yield load, and then some amount of plastic deformations will happen in front of the notch. And then you will find that in front of the notch some plastic deformations will happen, and then some portions will be there which where the brittle fractures will happen. Then again at the end portion, as the plane stress condition will reaches, then at this particular condition some ductile fractures will happen, and therefore you will find that the propagation energy will be a little bit significant. Okay. At the intermediate temperature region. At a very high temperature regions, you will find that the yield load will be there, the maximum load will be there, the fractures load will be there. Okay. And then the significant amount of propagation energy will also be there. That means the zone of brittle fractures will gradually reduce if you increase the temperature. So that was the schematically obtained data, and that is the experimentally obtained data. So you can think of these things. Okay. Like high temperature to very low temperature to intermediate temperature. Okay. So all these things you can find. Now if you able to measure the impact energy, okay, by reading the dial, then, and if you plot the data, then you will find that the impact energy absorption capacity will vary with temperature following this particular curve. Though this curve is a continuous curve, but generally we get the data in this particular fashion. So I need to plot the uh, uh, I need to show this particular plot where the starred as the scattered data. Means you need to do the test, multiple number of tests like 15 to 20 tests in order to obtain the continuous curve. Okay. Means first you need to obtain the scattered data. Okay. And for getting the each data you have to do the test, the number a number of lump sum number of tests, and then you have to plot those points where the x-axis represents the temperature variation in temperature, y-axis represent the energy absorption capacity or the impact energy. Okay. And then if you join by suitable fitting equations, then the curve will be like this, look like this. And here if you see this particular graph very carefully, you will find that beyond a certain temperatures the curve will flatten. So that particular region is called the upper self regions, where the fractures that will happen more or less ductile fracture in ductile manner. Below that particular critical temperature, that means the change in ductile fracture to brittle fractures will happen, and that will reflect on the fracture surface. Means by changing the, you know, the ductile fracture region or incorporating some brittle fracture region just the middle of the specimen. Okay, and then when it reaches to a certain critical value, you will find that the whole fracture surface has happened, the whole fracture surface is completely brittle fracture. Okay. uh, Okay, so in that way, you can categorize the different zone like ductile fracture zone, which is called this upper self region, the brittle fracture zone, which is called the lower self region, where the minimum amount of energy will absorb by the material, and at the transition zone, where basically this transition ductile to brittle or brittle to ductile transitions will happen. So that is called the transition zone. Okay, now if you apply the impact loading condition now, so then this particular transitions generally happen quite sharply. But if you apply the load where the shear kind of fractures happen, then maybe the curve will vary. For same material, the curve will vary in this way. So I will talk about these things in details in later on. Now here, I have showed the two different materials, that how these two different materials curve will vary. Okay, like the how the upper self energy will vary, how the lower self energy will vary, how the transition temperature zones will vary. So that things has been reflected in this particular curve. Okay, so once we have plotted this particular curve, so along with upper self energy, lower self energy, and the, the transition zone, we can also evaluate some factors like the impact energy, Charpy impact energy, the ductile brittle transition temperatures energy. We can also, analyze those things. Okay, so when we talk about the ductile to brittle transition temperature, that is called the DBTT temperature, then what we can calculate, first we ever find out the upper self energy, lower self energy, then we can average it out, and then whatever average energy is absorbed by the material at a suitable temperature, so that particular temperature is called the ductile to brittle transition temperature. So here, what will be the ductile to brittle transition temperature? So if you do the average of upper self and lower self energy, then we will find that this temperatures will be more or less 10 degree. Okay, so if we do this calculation, then we can correctly or accurately calculate that particular temperature. So in industry, people try to evaluate this ductile to brittle transition temperature based on their requirement, means where they are using this material, and that particular condition or that particular environment condition, what should be the maximum energy, what should be the minimum energy absorption capacity should there in the material. So considering these situations, industry peoples or the researchers or the, you know the research lab, they try to develop the material. So here, intentionally I put these two curve to show you that how this upper self energy will vary and how the dBdt will vary. Here, depending on the upper self energy, we can also think of that the dBdt energy will also vary. It is not that a material which shows the high upper self energy, but you know if it has the high upper self energy, then the ductile to brittle transition temperature will shift to the right direction. But if we want to develop the material and the material is will be acceptable to all of us or to all of the research community, then they demand to show the material which have the very low ductile to brittle transition temperature and very high upper self energy. That means the this energy should be very high and the curve should shift at the left direction. Okay, but sometime this dBdt will mislead by the high upper self energy. If we see this particular graph here, if you can find that for B sample the upper self energy is low, but if you are able to calculate the dBdt by average it out the upper self and lower self energy, you will find the dBdt will be very low as compared to the sample A. Okay, so that is why sometimes the procedure of measuring the dbt is mislead, to evaluate the material behavior or to evaluate the material performance or to evaluate the material, load bearing capacity at different temperature. So here is the real examples like how at the different temperature regions how the fracture morphology is varying, whether it is macro fracture morphology or micro fracture morphology. So that is the real examples. If you see the very low temperature test, then you can find that at very low temperature the fracture morphology will be looking like this. If you see the micrograph, then you can find the brittle fracture that would be looking like this. If you see the sample fracture surface which happens at high temperature, then this kind of fractures will happen. If you see the fracture micrograph, then some ductile kind of fractures where void will exist, where ductile void and the micro void will exist. So in that way you can characterize the fracture surface and you can correlate the energy absorption capacity at different temperature. If you have the ductile fracture mode, then the materials will absorb more and more amount of energy, because when the material deform under the plastic region, then the area under the curve will be much much more. If you see the load versus displacement curve, then you will find that at high temperature the area of load versus displacement curve will be more as compared to the load versus displacement curve at very low temperature. Okay, so that things also helps us to evaluate the impact energy at low temperature as well as at high temperature. And here that I was talking about, that if you do the test at high temperature, then the shear lip zone, the side zone is called the shear lip zone, where the shear kind of fractures has happened. This shear lip zones will develop, and that will actually associated with, or that things will contribute the propagation energy. Okay, so whatever propagation energy we have showed in the load versus displacement curve, so that particular propagation energy will comes from this particular shear lip zone. Okay, that means when the fracture zone will reaches at this boundary of this zone, then the remaining part will fractured by this shear deformation mode. And during this shear deformation mode fracture, whatever energy will absorb, so that particular energy is the propagation energy. Okay, so that things you need to consider. Here also I have tried to show you that how this red zone, that is the brittle fracture zone, spread out depending on the temperature. If you do the test at room temperature, then you can find out the shear leaf zone is significant. Though for some material, even room temperature is not sufficient to fracture a completely ductile fashion, but some amount of brittle fractures will be there. If you increase the temperature more than room temperature to very high temperature like 100 degrees centigrade temperature, then you may find that these red zones will completely diminish and the whole zones will be dominated by the yellow portions, that is the ductile portions. So such that the materials will absorb very high amount of energy. Now, apart from this temperature, the variations in temperatures, you can also find out that how the the strain rate can influence the fracture behavior. So, if you compare the two fracture surface, like for same material, one sample has tested under tensile mode, or where the strain rate is very very slow, that is 10 to the power minus 4 order. One samples, if you do the test at moderately strain rate conditions for 10 to the power minus 1 order, and one sample if you do the test at 10 to the power 3 order, not minus 3, 3 order, then how the fracture surface would be look like. Okay, so that things can be characterized properly. And if you see the microstructure, then you can think of that how this fracture mechanism or the fracture's behavior will change. Here, these two sample you can only think of, because here this sample is the different samples for different composition material. So you cannot compare this curve, this curve, and this graph, this graph, and this graph. But here these two graphs are for same materials, but the different strain rate, and how you can see that for different strain rate how this deformation mechanism is varying. So basically, I want to tell you that depending on the strain rate and depending on the temperatures, you can change the fracture morphology, you can change the deformation mechanism, okay, and you can change the energy absorption capacity of the material, and that actually reflect on the practical cases or in the service conditions where the material fail at different environment condition and the different loading condition. So in order to assess that the material performance, recreating these things in laboratory scales, we try to do this impact testing and try to understand or try to evaluate the impact energy, try to draw the impact transition curve, try to analyze this curve to evaluate the upper self energy, lower self energy, ductile to brittle transition temperature, and other different factors. So, what are the other different parameters that we can evaluate from this particular curve? If you plot the curve impact energy versus temperature, then we can find out the curve will vary like this, where upper self, lower self, dBTT, all these things we can evaluate. We can also, evaluate this transition curve if we measure the fracture area of cleavage fractures, the area of ductile fractures, then we can find that at low temperatures, the fracture surface which will be completely brittle. So that particular point, like T5 temperature, is called the nil ductility temperatures, where no ductile fracture surface is there. So that particular things is called the nil ductility temperature. So we can draw the fracture the transition curve in terms of the fracture surface or in terms of the energy absorption capacity. So the dotted curves is reflect the transition curve considering the fracture morphology or by measuring the cleavage fracture surface. So here you can find the few important parameters like nil ductility temperatures, FATT, the fracture appearance transition temperature, that is the T2 temperature, where the 50% cleavage fracture is there and the 50% ductile fracture is there. That means if you do a n number of tests at in different temperatures, and if you are able to measure the area of cleavage fracture surface, then you will find that at a particular temperature, that is T2, you will find that 50% cleavage fracture is there and 50% ductile fracture is there. Then this particular temperature is called the fracture appearance transition temperature. So people also, the industry people or the CSR peoples or the researchers, they also, try to ask the students or researchers to evaluate the FATT, the fracture appearance transition temperature of a material to assess the material performance. Okay. Now, if you do the test at a very high temperature where the fracture surface is completely ductile, means no brittle fracture is there. So that particular point is called the FTP. That is fracture transition plastic. That means when the ductile fracture is completely convert to brittle fracture is completely convert to ductile fractures, then that particular temperature is called the fracture transition plastic. Okay, so in that way you can evaluate these parameters to assess the material performance. Now sometimes people's, or sometimes, like if I talk about the naval grade steels, where the ships can develop, and by using those steel, the ship and hull can develop. So sometimes in order to develop those materials, they assign that the materials should have the energy absorption capacity at minus 40 degrees centigrade, and that particular energy should be a certain values. So that means they have fixed the impact energy values, let's say CV, and then they ask the researchers to evaluate the to evaluate the temperature, which should be well below their specified temperature. Okay, so let's say they have assigned that the material energy absorption capacity should be 60 joule at minus 40 degrees centigrade. So 60 joule is fixed. So as per their design criteria, they fixed the 60 joule. Okay, and they ask the peoples to evaluate the temperature that should be well below minus 40 degrees centigrade. If the material show the energy absorption capacity of 60 joule, which is well below at minus 40 degrees centigrade, then the material will be accepted by the designer people. Okay, and if it is go above that 40 degree, okay, minus 40 degree, then they will reject the material. Okay, so in that way, the development of materials generally carried out. So therefore, following this particular fashions, you can also think of the 57 joule ITT. You can evaluate the impact transition temperature considering the 60 joule, 40 joule, 27 joule. So as per their requirement, we can also evaluate the impact transition temperature. That means ITT, considering the energy requirement. Okay. Okay. Now. So here, I think till now we have covered the variations in impact energy, the fracture morphology, and how we can evaluate the impact energy. What is the correct procedure? What are the standard procedure? Okay, so all these things we have covered. Now, if we are unable to maintain the standard specimen, then and then again, if we fabricate the impact specimen, then how the energy will vary depending on the specimen geometry. So let's say I am talking about the variation in thickness of the specimen, Charpy specimen. So if you just plot the energy variation with varying the specimen thickness, then here you can find that if you have the small thickened specimen, then the dBTT or the dBTT will be very very less as compared to the specimen which have the high thickness. Okay, so that means here following this particular curve, you can clearly understand that how triaxiality is important for measuring the ductile to brittle transition temperatures or the impact transition temperatures like 27 joule ITT or 54 joule ITTs or 60 joule ITTs, something like that. Okay, so that means if you are unable to maintain the stress triaxiality, whatever impact transitions values you are evaluating, so that values is overestimating values. Okay, so that things you need to keep in mind. So is that clear to you? Hello.
Yes, sir.
So please follow this particular curve very carefully. Now here two graph I have plotted. Like one graph is based on the energy absorption capacity, and another no sorry shear fracture means the percentage of fracture. Okay, whether it is ductile or brittle. So that is why you will find that the curve upper and lower positions is fixed. But if you are able to measure the impact energy absorption capacity, so there you will find that along with the dBTT or ITT values, impact energy transition temperatures values, you will find that there will be certain variations in upper self energy also. Because for very small sample, the load bearing capacity will be small. So therefore, I will find the samples which have the thickness of 1.25 mm. Um, it absorbs a little bit low amount of energy as compared to samples which have the thickness is 10 mm. That means if you follow the standard procedure, then whatever energies are absorbing or whatever ITT values or impact transition temperatures values are getting you are getting, so that values will differ significantly as compared to the specimen which you have fabricated following non-standard fashions. Okay, so that things will reflect. Now till now, whatever the things we have discussed, we mainly discussed on the sample which contained or which have the BCC or HCP crystal structure. That means this impact transitions curve will also vary on material to material. Like one's material which have the the BCC crystal structure, or once material which have the FCC crystal structure, then the curve will also vary. One material which have the completely ceramic, one material which has the polymer kind of material, so that will material will also show the different type of curve. Okay, so that means the fractal transitions behavior can also vary from material to material. Okay, so now I will show you that how from different material that things will vary. Like if you have a material which contains the FCC crystal structure, that is face centered cubic material, just like austenitic stainless steel or copper or aluminium. So for that particular materials, if we do the impact test, then you will find that impact energy absorption capacity will vary depending on temperatures like this. Okay, but if you see, or if you do the transitions curve impact test for materials like steel, like high strength steel, the ferritic steel, or the low carbon steel, or the structural steel, then you will find that the curve will vary like this. Means the impact energy absorption capacity will vary with temperature following this particular curve. That means the transitions happen quite sharply, whereas in case of FCC material, this variations is insignificant. Okay, so why insignificant? So that is the big issues, or the, if you want to go into details, so that means um, there is a vast metallurgy is available. Like for FCC materials, it is very soft, and the slip system is significant. Means the slip planes, close pack slip planes is there, close pack slip directions is there, as compared to the BCC material. Okay, so if you have any interest to go into details about that, so they may go to study about the slip plane, slip direction, close pack slip planes, close pack slip directions. Okay, so you can study that. Okay, and then you can ask me in the next class, or in the subsequent class, that sir, why these things can happen. But the main things is that for BCC material, it is basically temperature sensitive material. Means the energy absorption capacity is highly sensitive with the temperature. That is because certain stress component is there in the material, BCC material, that is highly sensitive with the temperature. Okay, if you reduce the temperature, then this particular stress component will change depending on the temperature. That means the contribution of energy absorption of the by this particular stress component will be negligible at very low temperature. So that is why at low temperatures you will find that energy absorption capacity will be very, very less. Okay, and how these things will vary, that is also related with the movement of the dislocations. Means at low temperature, you know for BCC material, the movement of dislocations will be restricted. Okay, that means no plastic deformations will happen. Once the crack will happen initiate, the material will suddenly fractures by bond breaking actions. But for FCC material, though you are applying load at very low temperature, but in that particular cases, before bond breaking, materials atoms will prefer to glide over the slip planes. So that is why the plastic deformations will happen significantly in FCC material. And if you see carefully, the closest pack plane and closest pack direction, FCC material contain the highly closest pack plane and highly closest pack directions, where in case of BCC and HSP materials, the closed pack planes are, the packing density will be very, very less. Okay, I think material mechanical peoples or production peoples, they may understand these things quite clearly. But for civil peoples, they may go into details about these things a little bit. Okay. Now, apart from the material to material, these things can also vary with varying the microstructural parameters. Like For steel materials, it contains the different microstructures. For aluminum and copper material, it can also contain the different microstructures. For alloys, it can also contain different microstructures. So depending on the microstructure, this curve can also vary. The sharpness or the steepness or the slope of this transition portions will also vary, and that also decides that how this transitions has happened, whether it is happens quite sharply, whether it is happens gradually. So that things can be depend on the microstructural parameters like grain size, the phase fractions, and all that. Some compositions, material compositions also vary this transition curve. Okay, like if you have the carbon steel and you can change the carbon percentage of the material, then you will find that depending on the carbon percentage, the upper self energy dBdt will also vary. Okay, so overview you can think of. No need to go into detailed about that, because if you go into detail, then the course will be very long. Okay, but just overview you need to think of. The notch direction can also have can also influence the curve. Like if you fabricated the notch, the samples from the plate, but the plate have the rolling direction in a particular orientation. Okay, and if you fabricate the specimen in different orientation, then you will find that depending on the orientation of this particular notch, the energy absorption capacity will also vary. So so here how this thing is varying, so that thing is also related with the microstructural parameters. Because if you have the samples which have the microstructure which is quite homogeneous, means the equiax microstructure is there, and then if you roll that particular sample, then the equiax microstructures will change to ellipsoid microstructures. Okay, and then if you put the notch at a particular direction, that means you are intentionally focusing the crack propagation direction should happen along the rolling directions or along the transverse directions. Then you will find that the grain boundary area will change at the rolling directions, along the transverse directions, along the even thickness direction, and depending on that, your energy absorption capacity will vary. ও বাবা ক্লাস এখনো শেষ হয়নি তুই বাউল করে বেড়াচ্ছিস So here this is another examples for how for different materials how this curve will vary. Okay, now this is another important examples where I have reflected that though you are fabricating the Charpy impact specimen, but sometimes in considering the real scale situations, sometimes that particular values will mislead the the material performance, because in that particular cases you are fabricating the specimen that is 10 cross 10, but sometimes you will find that in real scale your plate thickness is more than 25 thickness, 10 thickness, 25 thickness, even 50 thickness. Sometimes you will find that the thickness of the plate is more than 100 so then people have found that though but you have calculated that impact energy absorption capacity at at room temperature. Let's say room temperature, you are getting certain values, but you are not extrapolating that values considering the practical thickness of the material. Okay, whatever value you are getting in Charpy impact testing, so that value is not matching with the practical sense. So in order to find out the what will be the probable reasons, so then people try to develop the other test such that they can evaluate the impact transition curve, and they can evaluate these temperatures and energy values quite accurately. So overall, people have found that if you have very thick material and if you are able to measure the impact transitions curve, then you will find that whatever curve you have drawn following the earlier test like Charpy impact test, so that curve will be situated far below that particular curve. Okay, that means whatever energy or dBdt you are getting, so that are overestimated values. Okay, if you compare the real scale situations, then you have to do the test considering the real scale thickness, um, and then if you whatever value you are evaluating, so that value will be comparable considering the real scale situation. Okay, what will be the probable results for changing these things? Of course, the stress triaxiality is the important part. Okay, though at very low temperature, at in front of the notch, high stress triaxiality is maintained, but even room temperatures, you may not be able to maintain the high stress triaxiality. That is why for some materials at room temperature also, or at even high temperature, you are getting the ductile fracture. But if you increase the thickness of the material, then again you may get the brittle fracture for that particular material. Then one can ask us that, sir, then why we need to go for Charpy impact testing? Now, the answer would be that Charpy impact testing is quite a rapid test. Industrially, we can do the test very rapidly. We can assess the material under impact loading conditions quite rapidly. Okay, without investing lots of money. Okay, but for stringent condition, that particular test is not suitable. Then we need to go for we need to invest more and more amount of money. We need to invest the money to set out
হ্যালো।
to prepare the setup such that we can do
হ্যাঁ, মানে
the
আমি
test
আজকে
considering the
আসতে
high
পারবো না। আমি
thickness of the
ওটা
material,
সোমবার কালেক্ট করতে পারবো।
and then we can invest
হ্যাঁ,
or we can
থ্যাংক ইউ।
use lots of material. Okay, and then we can do that test. Okay, but here for Charpy impact test, readily we can do that. Yes, but that particular test result is not the material property. Okay, roughly we can assess the material, roughly we can judge the material. Okay, but for actual case conditions, we need to go for other testing process. So I think in the next class we will talk about the other
হ্যাঁ স্যার,
testing
বুঝতে পারছি।
process
আর ভেঙে যাবে।
in detailed fashion. We can also talk about the flexural test, like as till now we have talked about the 3 point bend test or 3 point impact test, 3 point loading conditions for material. But for ceramic materials, how they are evaluating, how they generally evaluate the flexural strength or the strength of a material under 3 point loading conditions or the 4 point loading condition, considering the brick or considering the concrete beam. Okay, and then how the civil peoples or the construction peoples, they try to use this data, the flexural strength data, to design to design a building, to design a long beam, um, and all that. Okay, so we will talk about these things later on. Do you have any questions?
নো স্যার।
না
Hello.
স্যার, আজকে নিয়ে আর কিছু কোয়েশ্চেন নেই।
So I will share these slides later on. ঠিক আছে? তোমরা I know, I think it would be difficult to you to understand the factors that can influence the impact transitions behavior, because that is related with some metallurgical aspect. So I would suggest you don't worry about the detailed of the metallurgical aspect, but some overview you need to know, some overall factors you need to know. So that is why I just touch upon that, and I just try to tell you about the factors, and that generally influence on the material, mechanical properties. So you please go through the slides, and the related part you please go through in the book of detail. Okay, and you please collect the previous year questions. I think if previously I think this course, তমজিৎ এর আগেও কখনো কি কোর্সটা চালু হয়েছিল?
নো স্যার, নো স্যার, আমাদের বাড়ি প্রথম।
ফার্স্ট টাইম।
তোমাদেরটাই প্রথম না?
ইয়েস স্যার, ইয়েস স্যার।
ওকে ওকে।
ওই জন্য স্যার যদি বলছিলাম, মানে যদি পসিবল হয় স্যার একটু স্যাম্পল কোয়েশ্চেন্স বা মানে মানে কিরকম স্যার কোন পার্টগুলো একটু।
তোমাদের ক্লাস টেস্ট নেওয়া হবে লেটার অন। ওকে, যদিও অন্যান্য বা তোমাদের হয়তো ক্লাস টেস্ট গুলো নেওয়া হয়েছে, বাট ওপেন ইলেকটিভ ক্লাস টেস্ট একটু পরে নেওয়া হবে। ইট উইল বি ডিসাইডেড বাই আস। ওকে, একটু কভার করে নিই, ফলে তিনজন ফ্যাকাল্টি আমরা আছি।
হ্যাঁ স্যার।
প্রভাস স্যার কি কিছু বলেছেন যে ক্লাস টেস্ট কবে নেবেন কি না নেবেন?
না স্যার, ডেট নিয়ে উনি কিছু বলেননি স্যার।
আচ্ছা, তো কভার হয়ে যাওয়ার পরে আমরা যখন ক্লাস টেস্টটা নেব তখন ওই ক্লাস টেস্টের কোয়েশ্চেন দেখে মোটামুটি তোমাদের একটা আইডিয়া হয়ে যাবে যে কি ধরনের কোয়েশ্চেন হতে পারে, ঠিক আছে?
স্যার ক্লাস টেস্টে মানে ওটার আগে বলছিলাম যদি স্যার মানে মানে একটু তো মোটামুটি
দেখো
যেরকম
আমি
স্যার পড়াচ্ছেন এখান থেকে
হ্যাঁ,
কোন জোন গুলো বেসিক্যালি আমরা বেশি করে আর কি ফোকাস করবো ওইগুলো একটু বলে দেবেন।
মেইনলি তোমরা টেস্টিং প্রসেসটা একটু ফোকাস করার চেষ্টা করবে। হ্যাঁ, আমি যে টেস্টিং প্রসেস গুলো আমি বলার চেষ্টা করছি, টেস্টিং প্রসেস গুলো একটু ফোকাস করবে, আর একটু ফ্যাক্টরস গুলো মানে যে ফ্যাক্টর গুলো মেকানিক্যাল প্রপার্টিকে অল্টার করে ওভারভিউ গুলো দেখার চেষ্টা করবে, নট নিড টু গো ইনটু ডিটেইল। ওকে,
ওকে স্যার।
and how we can analyze that mechanical properties, so those things you need to think of, like আজকে যেমন বললাম যে ইমপ্যাক্ট প্রপার্টি যে আমরা ইভালুয়েট করি, সেই ইমপ্যাক্ট প্রপার্টির ক্ষেত্রে আমরা কি কি জিনিসগুলো দেখি। হ্যাঁ, স্যাম্পল ফেব্রিকেশন, মেশিন কিভাবে আমরা অপারেট করি। হ্যাঁ, যদিও এখানে আজকে আমি একটা জিনিস বলতে ভুলে গেছি, লাইক যখন আমরা লো টেম্পারেচার টেস্ট করি তখন যে বা ওই লো টেম্পারেচারকে আমরা কিভাবে কন্ট্রোল করি। So basically we need to prepare some solutions, like we use liquid nitrogen, we use methyl alcohol or ethyl alcohol, and then we prepare some solution such that we can maintain the low temperature till minus 196 degrees centigrade. Okay, and then we immerse the samples, we hold the sample in this particular solution certain period of time, at least 5 minutes to 10 minutes, such that the temperatures of the samples, temperatures of the solutions will equilibrate, and then once the temperature is equilibrate, then suddenly we catch the samples using the tongs, and then we suddenly put over the anvil, and quickly we do the test, means within 5 seconds we try to do the test to get the impact energy values. So এই যে প্যারামিটারস গুলো যেগুলো আমি বলছি সেগুলো একটু মনে রাখার চেষ্টা করবে, একটু পড়ার চেষ্টা করবে, এন্ড দেন আমরা কিভাবে যে ডেটাটা পেলাম কিভাবে আমরা ওটাকে রিপ্রেজেন্ট করি, লাইক বাই প্লটিং সাম কার্ভ, এনার্জি ভার্সেস টেম্পারেচার কার্ভ। যদি আমরা এনার্জি ভার্সেস টেম্পারেচার কার্ভ থেকে আমরা কি কি জিনিস পেতে পারি, লাইক ইম্প্যাক্ট এনার্জি, আপার সেলফ এনার্জি, লোয়ার সেলফ এনার্জি। তারপর হচ্ছে যদি আমরা টেম্পারেচারের পার্সপেক্টিভ ধরি, লাইক ডিবিটিটি, এফএটিটি, হ্যাঁ, যেমন 27 জুল আইটিটি, 54 জুল আইটিটি, 60 জুল আইটিটি। সো এই যে টেম্পারেচার গুলো হুইচ ইজ কল্ড দ্য ইম্প্যাক্ট ট্রানজিশন টেম্পারেচার, সো এই টেম্পারেচার গুলোকে আমরা জেনারেলি ক্যালকুলেট করি। সো হয়তো বলা যেতে পারে যে ড্র দি ইম্প্যাক্ট ট্রানজিশন টেম্পারেচার কার্ভ, and and make some points over that what are the important parameters or what are the important values we can evaluate from this curve. Okay, লাইক যেমন টেনসাইল টেস্টের ক্ষেত্রে আমরা বলেছিলাম যে যদি বলি যে একটা টেনসাইল ইঞ্জিনিয়ারিং বা ট্রু স্ট্রেস কার্ভ ড্র করো, অ্যান্ড দেন ওই কার্ভ থেকে যে ইম্পর্টেন্ট পয়েন্টস গুলোকে, ইম্পর্টেন্ট স্ট্রেন পয়েন্টস, এগুলোকে তোমরা পয়েন্ট আউট করো ফ্রম দিস কার্ভ। হ্যাঁ, এরকম বলতে পারি। তো তারপরে হয়তো এরকম বলতে পারি যে ইঞ্জিনিয়ারিং stress strain curve, what is the difference between engineering and true stress strain curve? So then you have to explain that why this difference can happen. Okay, so all these things you can think of.
ওকে, থ্যাংক ইউ স্যার। থ্যাংক
স্যার
ইউ।
এমনি ফ্যাক্টোগ্রাফির অ্যাসপেক্ট থেকে মানে কি টাইপের কোশ্চেন আসতে পারে?
ফ্যাক্টোগ্রাফিক অ্যাসপেক্ট থেকে যেমন ধরো ওই যে ইম্প্যাক্ট ট্রানজিশন কার্ভ যেটা আমি ড্র করে দেখানো হয়েছে, সো ওইটা আমরা ফ্র্যাকচার পার্সপেক্টিভ থেকে আমরা ড্র করলে কার্ভটা কিরকম হতে পারে, এরকম ধরো কোশ্চেন দিতে পারি।
ওকে
যেটা ধরো
ফেটিক টাইপের জিনিসপত্র থেকে স্যার কিরকম হতে পারে স্যার, মানে আমাদের
ওইটা তো স্যার করাচ্ছেন, ফলে স্যারকে বললে কি স্যার বলবেন। ফ্যাটিকের ক্ষেত্রেও আমি বলবো যে যদি আমি পড়াতাম হয়তো আমি বলতাম যে ফ্যাটিক টেস্টকে আমরা কি কি ভাবে করতে পারতাম, বা ধরো যে টেস্টিং প্রসেস কে আমরা কিভাবে ডিজাইন করতে পারতাম, লাইক ফ্যাটিক এমন তো নয় যে শুধু কম্প্রেসিভ টেনসাইল এই দুই ধরনের ফ্যাটিক মানে অ্যাপ্লিকেবল। Sometimes compressive fatigue can also be carried out. Tensile fatigue can also be carried out. মানে bending fatigue can also be carried out, like, you know, rotating fatigue can also be think of. Okay, so there are lots of fatigue testing, you know, procedures available as per the standard. Okay, so I may ask you some questions like, please suggest us to design some, you know, fatigue testing machines such that we can evaluate the material performance under fatigue loading condition and under, you know, different types of fatigue loading condition, not only the uniaxial loading condition, by also, you know, we can think of like bending kind of situations. Okay, where, you know, repetitive loading is applied. Okay, যদি ধরো বেন্ডিং টাইপ অফ লোডিং এর কথা বলি, তাহলে ধরো তুমি একটা ওয়্যারকে যদি বারবার যদি, ইউ নো, মানে বেন্ড করতে থাকো না, দ্যাট মিন্স ওয়ান সারফেস ইজ ফেসিং টেনসাইল কাইন্ড অফ লোডিং, simultaneously that same surface is facing experiencing the compressive kind of loading. সেই জন্য যখন একটা ওয়্যারকে বারবার বেন্ড করতে থাকো না, so then certain period of time you will find that your wire has broken. So এই পার্টিকুলার যদি এই পার্টিকুলার জিনিসটাকে যদি তুমি, ইউ নো, রিপ্রোডিউস করতে যাও ল্যাবরেটরি স্কেলে, দেন হোয়াট টাইপ অফ, ইউ নো, ফ্যাটিক টেস্টিং প্রসেস ইউ নিড টু অ্যাপ্লাই, ইউ নিড টু ফলো। সো আমি হলে হয়তো এই ধরনের কোয়েশ্চেন করতাম, what are the important parameters that we need to maintain or we need to check before fatigue loading? ওকে, তারপরে হচ্ছে ধরো যদি ধরো আমরা ইউনিঅ্যাক্সিয়াল ফ্যাটিক টেস্ট যদি করি, তাহলে সেক্ষেত্রে আমরা কি কি জিনিস ভ্যারি করতে পারি, লাইক যদি আমরা ধরো যে যদি স্ট্রেসের কথাই বলি, লাইক আপার স্ট্রেস, মানে ম্যাক্সিমাম স্ট্রেস আর মিনিমাম স্ট্রেস, এইগুলো আমরা কিরকম ভ্যারি করতে পারি। যদি ধরো আমরা টেনসাইল কাইন্ড অফ সিচুয়েশন ধরি, তাহলে যদি আমরা ম্যাক্সিমাম স্ট্রেসের ভ্যালুটা আমরা কত দূর পর্যন্ত বাড়াতে পারি, মিনিমাম স্ট্রেসের ভ্যালুটা কত মিনিমাম রাখতে পারি। হ্যাঁ, যদি আমরা ওয়ান কেসে যদি আমরা ওই গ্যাপটা কম রাখি, অ্যানাদার কেসে ওই গ্যাপটা যদি আমরা বেশি রাখি, তাহলে মেটেরিয়াল কিভাবে বিহেভ করবে। ফ্যাটিকে আমরা কি জেনারেলি আমরা ইভালুয়েট করি, ফ্যাটিক লাইফ ইভালুয়েট করি না ফ্যাটিক স্ট্রেংথ ইভালুয়েট করি। যদি ফ্যাটিক লাইফ ইভালুয়েট করি, তাহলে মেটেরিয়াল টু মেটেরিয়াল কিভাবে ভ্যারি করে, ফ্যাটিক লাইফটা আর কি কি প্যারামিটার উপরে ভ্যারি করতে পারে, লাইক ওই যে বললাম যে লোড গ্যাপ মানে স্ট্রেস গ্যাপ, ওকে, ম্যাক্সিমাম এন্ড মিনিমাম স্ট্রেস গ্যাপ, kind of, you know, stress, different kind of stress condition like compression, tensile compression, okay, tension compression, bending, you know, bending fatigue. So all these sort of conditions we need to think of, and then we need to correlate with the fatigue, you know, fatigue properties of a material, and try to correlate the factors. So এইগুলো তোমরা ভাবতে পারো।
ওকে স্যার, থ্যাংক ইউ। মানে স্যার, মানে ওভারভিউ গুলো মেইনলি, বেশি ডেপথে ইনডেপথে। আচ্ছা,
হ্যাঁ, বেশি ইনডেপথে হয়তো জানি না। তোমাদের স্যার কি ফ্যাটিক পড়িয়েছেন?
স্যার মানে জাস্ট আগের দিন স্টার্ট হয়েছে।
আচ্ছা, কি কি পড়িয়েছেন ফ্যাটিকে?
ফ্যাটিকে স্যার মেইনলি আগের দিন তো স্যার এসএন কার্ভ ওগুলো করাচ্ছিলেন।
হ্যাঁ, তো এসএন কার্ভে নিশ্চয়ই ফ্যাটিক লাইফ সম্বন্ধে একটা আইডিয়া দিয়েছেন, ফ্যাটিক স্ট্রেন্থ সম্বন্ধে কিছুটা বলেছেন।
ইয়েস স্যার।
হ্যাঁ, তো ওইগুলো। তারপর হচ্ছে ধরো এমনি থিওরিটিক্যালি এসএন কার্ভ কি করে ড্র করা হয়, যেগুলো আমি বলেছিলাম না, যে টেনসাইল টেস্টের সময় আমরা যে ডেটাগুলো পাই, সেখান থেকে আমরা ওই ডেটাগুলোকে আমরা থিওরিটিক্যালি প্রেজেন্ট করার জন্য কিছু ইকুয়েশন ডেভেলপ জেনারেলি করা হয়, আর সেগুলোকে রেপ্লিকেট করার জন্য এই ইকুয়েশনগুলোকে কাজে লাগানো হয়। সেরকম ফ্যাটিকের ক্ষেত্রেও দেখবে কিছু ইকুয়েশনস আছে, বা রিসার্চাররা ডেভেলপ করেছেন কিছু ইকুয়েশন, যেমন কফিন ম্যানসন ইকুয়েশন। আমি জানি না স্যার এগুলো বলবেন কিনা। হ্যাঁ, তো ওইগুলো যদি বলে থাকেন, তাহলে ওই ইকুয়েশনস গুলো জেনারেলি কিভাবে ডেভেলপ করেছেন, ডেভেলপ করতে গিয়ে কি কি অ্যাজাম্পশনস ওনারা ফলো করেছেন, সেই পার্টিকুলার ইকুয়েশন গুলো সব জায়গায় অ্যাপ্লিকেবল কিনা, এগুলো তোমরা একটু ভাবতে পারো। যদি পড়িয়ে থাকেন তাহলে ভালো, না পড়ালে তো কোনো ব্যাপার নেই।
গ্রিফিথস ইকুয়েশনটা স্যার আগের দিন দেখেছিলেন স্যার, তার আগে স্যার ক্রায়োজেনিক্স নিয়ে একটু বলেছিলেন একদিন স্যার।
তো গ্রিফিথ ইকুয়েশনে, যেমন গ্রিফিথ ইকুয়েশনটা হচ্ছে কোন কোন মেটেরিয়ালের ক্ষেত্রে অ্যাপ্লিকেবল। গ্রিফিথ ইকুয়েশনে আমরা যে ফ্র্যাকচার স্ট্রেসটা ইভালুয়েট করি, সেই ফ্র্যাকচার স্ট্রেসের ভ্যালুটা কার কার উপরে ডিপেন্ড করবে, লাইক ধরো ক্র্যাক লেন, হ্যাঁ, তারপর হচ্ছে তোমার ওই যে সারফেস এনার্জি ভ্যালুজ, দ্যাট ইজ গামা ভ্যালুজ, হ্যাঁ, For brittle material, gamma values is fixed. Okay, but is it same for all material? Like if we go for ductile material, like um, for steel or high strength material, then can we put the gamma values directly? Um, okay, then what will be the difference? Will the Griffith equations follow for ductile material? Yeah. Griffith generally developed করেছিল for brittle material, মানে highly brittle material,
Perfectly brittle
for
material.
perfectly brittle material, for glass. মানে if I say glass material এর ক্ষেত্রে it is applicable. Then to evaluate the fracture, fracture strength, Griffith has modified later on. No, Griffith নয়, মানে Griffith Orwan has developed
Yes.
another equation. Okay, using the Griffith model. Okay, how they have developed that particular equation. Okay, how they have incorporated the surface energy. Okay, like gamma in terms of gamma p and gamma e in terms of simple gamma, how they are trying to get the quite accurate value of gamma sigma f, that is fracture stress value. So all these things you can study, you can think of. আর কিছু?
Okay. Thank you. No, thank you.
ঠিক আছে,
বলছিলাম যে আপনার পার্টে স্যার কতটা থাকবে, মানে কত মার্কস থাকবে?
সব 30 মানে ইকুয়াল মার্কস মোটামুটি থাকবে।
আচ্ছা, ওকে।
আমি একটু ডিটেলসে পড়ানোর চেষ্টা করছি, জানি না স্যার কিরকম পড়াচ্ছেন। তো যদি তোমাদের মানে কোনো কোয়েশ্চেন থাকে এগুলো একটু জানাবে পরে, এখন নয়, হয়তো আগে পড়িয়ে নিই, হ্যাঁ, লাস্টের দিকে হয়তো একটু ডিসকাস করা যেতে পারে।
Okay, sir. Okay, sir.
থ্যাংক
স্যার
ইউ।
মানে
এমনি
আপনার পার্টে কারো কতগুলো ক্লাস মোটামুটি আমরা পাবো?
আমি ইমপ্যাক্ট টেস্টটা কমপ্লিট করার চেষ্টা করব, তারপরে এনডিটি পার্টটা মানে নন ডিস্ট্রাকটিভ টেস্টিং পার্টটা করাবো। আই থিঙ্ক মেকানিক্যাল পিপলস দে মে নো অ্যাবাউট দিস থিংস। ওকে, তোমরা কি জানো তমজি?
স্যার এইবার ল্যাবে আছে, কিন্তু এখনো স্যার ওই ল্যাবটা মানে হয়নি, ওই ল্যাবটাই আছে।
আচ্ছা আচ্ছা
এবার মেশিন এলিমেন্টস ল্যাব নামে একটা আছে স্যার, ওখানে আছে।
হ্যাঁ স্যার।
আচ্ছা আচ্ছা, তাহলে তো তোমরা এই জিনিসটা আরো ভালো করে হয়তো জানতে পারবে।
স্যার
থিওরিটিক্যালি
এখনো মানে কিছুই জানি না বেসিক্যালি, কারণ স্যার ওটা হয়নি, আমাদের মানে থিওরিটিক্যাল পার্টটা সেরকমভাবে কভারও হয়নি স্যার। মানে
ও ও ঠিক আছে, তো এনডিটি পার্টটা আমি কভার করার চেষ্টা করব, আর যদি সময় পারমিট করে তাহলে ওয়্যারটা একটু হয়তো পড়ানোর চেষ্টা করব। ঠিক আছে, আর আরেকটা হচ্ছে আমি হয়তো এতদিন মানে মেটালোগ্রাফি সম্বন্ধে অনেক কিছু বলে গেছি, যেটা হয়তো অনেকের কাছে ক্লিয়ার নয়। আমি মাইক্রোস্ট্রাকচারের একটা স্লাইড বানিয়েছি, যে হাউ ইট লুকস লাইক, হাউ উই ক্যান ইভালুয়েট দ্য মাইক্রোস্ট্রাকচার ফর for and how after evaluating the microstructures or characterizing the microstructure, how we can correlate with the mechanical properties. So এই পার্টটা আমি একটু বলে যাব। হ্যাঁ,
ওকে স্যার, ওকে স্যার।
তাহলে হয়তো তোমাদের ক্ষেত্রে যে মাইক্রোস্ট্রাকচারের প্যারামিটারের কথাগুলো বারবার যেগুলো বলছে সেটা হয়তো একটু ক্লিয়ার হবে।
স্যার বলছিলাম মানে এই সাবজেক্টটা ক্লাস টেস্ট আমরা মানে কোন মানে এপ্রিলের ফার্স্ট উইকে না সেকেন্ড উইকে?
হ্যাঁ, একটু মানে কমপ্লিট করে শেষের দিকে নেওয়ার চেষ্টা করবো। হ্যাঁ,
মানে এপ্রিল সেকেন্ড উইক করে হয়তো হতে পারে, তাই তো?
হ্যাঁ হ্যাঁ হ্যাঁ, বলে দেবো, আগে বলে দেবো তোমাদের।
আচ্ছা স্যার, আচ্ছা।
আর স্যার এমনি তো স্যার এই কোর্সটার স্যার স্ট্যান্ডার্ড টেক্সট বুকটা হচ্ছে স্যার জিওর্জ ডাইটারের ওই বইটা, তাই তো?
হ্যাঁ 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 হ্যাঁ, ওই বইটা।
Okay, sir. Okay, sir.
ঠিক আছে, আর তোমরা একটু ওই সুবীর স্যার মানে সুবীর পাল স্যারের ক্লাসটা একটু করার চেষ্টা করো, হ্যাঁ, একটা টাইম বের করে স্যারের ক্লাসটা একটু নিও, কারণ যদি না করো না স্যার কিন্তু কোশ্চেন দিয়ে দেবেন, তখন তোমরা ফেসে যাবে।
ইয়েস স্যার, ইয়েস।
ওকে স্যার,
ঠিক আছে,
থ্যাংক ইউ স্যার।
ঠিক আছে, ঠিক আছে।
স্যার